the first collisions happened in the ISR, the Intersecting Storage Rings. So you heard from Carlo Rubbia at the initial clip saying that they were the first collider in history. And of course, this is true. We were celebrating last week with a symposium, and that was the beginning of his initial introductory speech. I'm here today with Dr. Steve Myers. Welcome, Steve, and thanks for joining us here today. Steve has had an incredibly long career at CERN, started exactly here in the ISR, but culminating with the LHC. So this man has seen all the colliders at CERN with their successes, their history. And your main role, the final role, was director for accelerators and technology, but you were specializing in operations of these accelerators. So Steve, do you remember this place?
I remember this place very, very well. I spent a lot of time here. This was point 4 of the ISR, and the ISR was the first ever Hadron collider. It collided in 8 interaction points, and this was one of the important interaction points where the so-called split field magnet was installed. And it's a real pleasure to be here today talking to you.
Yes, and today we are not only looking at the past with Steve and with other guests, we are also looking at the present, because right now in the LHC there are circulating beams, proton beams, for the very first time in 2 years. There were 2 years of a long shutdown. Steve, this is regular things. Accelerators, colliders need periods of rest. And this was a long shutdown for the LHC. What was happening in the last 2 years?
Well, every big collider, every big accelerator needs to have shutdowns. There's various things happen during a shutdown. The first thing, of course, is normal maintenance. You replace old equipment, and you also upgrade to improve the performance. And then, I mean, in order to do this, you normally take the whole machine apart. And many times when I walked around the LHC tunnel and saw all of the components on the floor, I thought, this will never work again. So it's a huge relief when you put the beam in and it goes round and round and round and works. And this has happened very recently in the LHC.
It has happened right yesterday, and among our guests we have Rende Sterenberg, head of operations at the Accelerator Control Center, who is with us right now, I hope, for a handshake, and then we'll talk to him later on, and you will be able to ask all your questions to our guests. Do we have the control center live? Yes, I see Rende. Yes. Hello, Rende. Do you see me? And do you hear me?
Yes, I hear you.
Okay.
So greetings from the CERN Control Center.
And congratulations to you for yesterday's performance. Can you just tell us very quickly what happened, and then we come back to you with more questions and more information later on.
Yes. So yesterday we actually culminated a lot of preparatory work by injecting the very first beams again in the LHC and make them turn in both beams counterclockwise then and clockwise. Now since 3:10 we have a few bunches circulating in the machine, and people are preparing all kinds of measurements. So we'll come back to that later, I assume.
Okay, thank you. Yes, we come back later. And I am now wanting to introduce to you our second guest, Romeo Perim. Good afternoon, Romeo. Thanks for joining us. So Romeo is also another super collider expert who, like Steve, started his career here in the ISR and ended the career at the LHC as well, but with a different specialization. What were you doing at the CERN colliders?
Well, at the CERN collider, I started with the ISR, designing the main magnets on the ISR and the auxiliary magnets. These were classical magnets.
And you brought us a piece. Yeah. I see something.
These were classical magnets, so made with copper coils. Mm-hmm. But what is, and then also I designed, made, in fact, constructed the split field magnet also. But these are classical magnets.
Yes.
But what was more interesting, and really an innovative thing made in the ISR, were the superconducting quadruples for the high luminosity insertion.
So you saw already in the 70s, you were talking about superconductivity and
yes,
higher luminosity.
Higher luminosity.
This is keywords for today, for the LHC.
Yes, this was in fact the basis you wanted for the LHC.
Yes.
And also it was possible in this way by building these quadruples and building this low beta or high luminosity insertion. it was possible to form a team of experts at CERN,
Yeah.
and also to form the industry, because the series production of the quadruples were made in industry.
Show me what you brought.
Well,
We can show it to the camera.
yes,
So tell us what this piece is.
yes, this is a quarter, in fact, one pole of a quadruple, which has 4 poles.
Yes.
And one can see the arch structure. In fact, the innovation was really the concept of the Roman arch, the compressing the coils from the outside and producing a compression on the inside of the. And this compression was to compensate for the tensile stresses, which would appear when the magnet is excited. And
Right.
coils of this type, they are very weak in tension, but very strong in compression. So we have to put inside a pre-compression just to eliminate the tensile stresses by producing compressive stresses inside.
So already this machine had a record-breaking machine because it was the first time in history that you collided
Yes.
protons, hadrons.
Hadrons.
First time that the superconductors were used in the magnets
Yes.
and with a very high performance.
Yes. In fact, these were the first superconducting magnets operating in an accelerator. It was the ISR, and they operated very well. It was a real breakthrough in the technology of superconductivity applied to magnets for particle accelerators.
And what was right here in this big hole where we are now?
Well,
Steve said this is one of the interaction points. So interaction point 4.
Interaction point 4, a very big, huge magnet, a split field magnet, was placed here. I was also the project leader for that big magnet.
So you know this place very well.
Yes, yes. And yes, one sees it now in the picture.
We can see, yeah, we can see the.
Yes.
So essentially, it's called intersecting storage rings because of this crossing of the
crossing, the
impacts.
two rings. There were 2 rings crossing in 8 points around the machine.
And this is one of
This
the
is point 4.
point 4, which was the
yes,
largest with this
Why
special
the superconducting insertion was placed in point 8.
I see. Okay, okay. So all this work that you did back then laid the foundations for our huge superconductor, the
Yes,
LHC,
the LHC.
27 kilometers of superconducting magnets.
Yes, this
so you
was
see a direct link between
Yes, there is a
the
direct
past and the
link
present.
because I started, in fact, the first prototypes for the LHC magnets, arriving also, introducing also the production in the industry. And then when I retired, I mean, all the development had already been done.
Yes.
So there was the same production to be done.
And it's not by chance that we could build a 27-kilometer superconductor.
Yes,
I want to give you a little present. Here I have, maybe you will recognize what it is. So let me show it first to the public. Yes? Can you tell me what this is?
Yes, this is in fact a cross-section of the main magnet of the ISR, the classical magnets,
Exactly. So
not superconducting.
we use this as a reflector that you can see in the dark. So when you bike in the dark or when you walk in the dark. And this is for you, but
thank you very much.
we also have these kind of gadgets for the viewers who are going to guess what this photo is. You know what it is, but don't say. You will say at the end of the presentation.
Yes.
That's not this one. Is this one? Right, yes.
Yes, you
So-
see, and I see also myself there.
This is a challenge. Guess what it is for you to guess or just approach an answer. What is this big object? And at the end of the presentations, we will reveal, and you will
describe.
say what is a good answer, good enough answer.
Yes.
You can send your questions via YouTube and Facebook together with the answer to this question if you want to participate and win an ISR memorabilia, let's say, which is also a very useful object. So we've gone through the operations, we've gone through the magnets. Romeo, come back when I call you for the question and answers.
Okay.
It's now time to talk about the physics of ISR. And at the symposium last week, we asked the question to one of the senior physicists of CERN, who, like Romeo and Steve, has done all his career here at the CERN colliders, but in this case, doing experiments. So Ugo Amaldi on the physics of ISR. Volume. We don't hear.
New particles, the Higgs boson, let's say. It was built just to understand for the first time collisions between two protons, what would they produce. And in the first few years, two important results came out by different groups, of course, in different interaction regions. In interaction region 1 and 8, the groups measured the total cross-section, that is the total probability that two protons collide. The theory at the time would say that this total probability would be constant with energy. It was expected to be very same as at low energy. Instead, we found that, and I was involved in one of these experiments, that we found that the cross-section in the ISR energy range would increase by 10%, which is a big effect. This was a big shock to the field and also obliged theorists to change the fundamental theory of this interaction. The second phenomenon which was discovered by the other three experiments, which were in region 1 and 2, was that when two protons collide, sometimes the point-like components, which now we know are quarks inside the two protons, would collide themselves and produce new particles at large angles with respect to the beam. This was completely unexpected. There was no special detector built beforehand to find and study this phenomenon, and this is what we call technically the discovery of large transfer momentum particles. This was announced in a big conference, important, in 72, and then published also in 73. This was the beginning, the very bright beginning. And then other results were obtained later on, but this is a long story. I think there's no point to go in detail now.
Okay, so this was Ugo Amaldi on the physics of the ISR. Basically, you learned what it means to collide protons and what happens in these collisions. But I also understood that the first hints of the existence of quarks and gluons was gathered at these collisions.
Yes, and this was a huge shock for everyone because most of the detectors were not, in the beginning, were not designed for that. And this changed the whole way in which proton-proton collider detectors were designed afterwards. And as a result of that, for example, the SPP bar S discovered the W and the Z, not only because of the ISR, but because of the results of the ISR that led them in the right direction. And I think this has been the case. I think the ISR has been the building block on which many of the colliders in the world have been built because it was such a successful collider.
Yes, we mentioned the word hadron. We mentioned protons, so protons are hadrons. But what exactly is a hadron?
Well, all hadrons are very heavy elements, very heavy particles. And when you collide these, of course, by making collisions, you make a huge amount of energy instead of if you do a stationary target, where if you hit them against a stationary target, the amount of energy is much, much less. Think of two trucks running into each other and the amount of energy they give off, and think of one truck running into a wall and going through the wall, much, much less energy. So the energy is usually the most fundamental parameter for discovery. And so therefore, hadron colliders are discovery machines, and that has been the case. I have only ever worked on colliders in my whole life.
Yes, the first colliders before this were colliding electrons, positrons that are very light particle. But as you said, these hadrons are really big bullets which produce a lot of energy, and energy against energy creates new matter and makes you find particles, which was the case because thanks to the expertise gained at the ISR, CERN made fundamental discoveries, two of them which got the Nobel Prize.
Yes.
And you worked at both colliders.
Yeah, the W and Carlo Rubbia for the W and the Z, and then later, well, we got the Higgs boson in the LHC, which was probably the most important discovery of this century.
Yes, and the most important discovery we did in the last, decades at CERN. This was a memorable time. I remember working closely with you when the LHC was pushing, ramping up the energy. And just a year after the discovery, we are seeing Fabiola Gianotti. At the time, she was spokesperson of the Atlas experiment, announcing the discovery. Today, she's the Director General of CERN. That day is a memorable day for me. It was just amazing. So, discovery machines bring us to the LHC, which, as we said, has pilot beams running right now. It's not yet the beginning of physics, right, Steve? As you said, there was a long period of upgrade and repairs. And why does it take so long to start up an accelerator of that complexity?
These colliders are incredibly complex machines, and they are also can be quite self-destructive because of the amount of energy there is in a beam. For example, a beam in LHC could burn a hole of several kilometers in metal.
Yeah.
And so you cannot afford that this beam is not totally controlled.
You have to steer it.
You have to steer it. You have to make sure that even the halo, the small amount of particles which come, don't reach the detectors, don't reach the superconducting magnets. And this is a very, very complicated way in which you have to go through. It's almost like a medical experiment where you have to make sure that no one ever gets irradiated unintentionally. So this procedure is very well established now, and that has to be gone through at the beginning of every new run or at the end of every long shutdown. And this is totally controlled by the people in the control room, who have to watch every single movement along the way.
Night and day.
Night and day.
And that's where we're going right now. We are going to the CERN Control Center to touch base again with Rende Sterrenberg, Head of Operations at the Large Hadron Collider. Are we with, yes, there you are. It's so reassuring to see you. As reassuring as was for you yesterday seeing the pilot beams making their way through the accelerator.
Yeah, exactly.
So can you just wrap up in a few simple words what happened yesterday, first day with beams in the LHC?
Yes, so the entire injector complex was already running. So they had already been for several months and providing beams to the fixed target physics. Now, what they did, they prepared this beam for the LHC. And then in the last 2 weekends, what we did as well was testing the beam lines that go down from the SPS towards the LHC. So one beam line for the clockwise direction, one beam for the counterclockwise direction. And then yesterday, we finished actually all the preparations for the LHC machine itself to be able to inject these beams. So that was done yesterday morning. We started with that. And then the idea is, so the LHC consists of sectors, and in 4 places of the machine we have experiments. So the idea was to inject the beam first in clockwise direction and then stop at the first experiment. So that we do by closing some collimators. We put some obstacle in the beam, and then the beam will be lost on these blocks. And then secondary particles which are generated from this have been measured and observed by the experiments. As soon as that was done, we went and the corrections were made. We went further on to CMS, and then further on to LHCb, and then further on to Atlas. And every time we repeated this. And then we did the same thing for the opposite direction. And once we knew that the beam was, let's say, could make the circle and was going around, we actually established circulating beams. And then a lot of work still has to be done, and which is now ongoing.
Now, what's the status?
So the status now is that we have 2 bunches circulating. And you see around, if you look around here in this what we call the island of the LHC, you see all these people working. There are some people working on the beam positioning monitors. So in order to be able to observe the position of the beam within the vacuum chambers, we have hundreds of monitors around the LHC that measure the position of this very tiny beam. So that's the team here, or the person here is working on that. His colleagues have now left a moment. And then the team next to it is working on the feedbacks. So as Steve already said, the beam can be destructive for the machine. So what you want to have is a perfect control of the orbit of the beam throughout the vacuum chamber. So what we do by measuring the beam with these beam position monitors, we continually feed back into magnets that steer the beam in order to maintain the beam in the center of the vacuum chamber. So that's the second team of people working on these renewed feedbacks, which we changed during the long shutdown as well. Another parameter which is very important to measure on the beams is profile monitors. Profile monitors allow you to measure the shape of the beam in the horizontal and the vertical direction. And that's the team over there that is working in order to make these profile measurements operational again. Okay. We have another team that is working. These are the few people in the middle, but there are a few others on another place in the control room. And those people are working on the optics of the machine. So in order to keep the beam focused and well guided through the vacuum pipe, you need to focus the beam continuously. And for this, you have to set the currents in hundreds and thousands of magnets. So we have therefore an optics team that is working on this in order to establish the best optics to keep the beam in a good condition in the machine. So that's what's presently going on, in fact.
That's great. And pilot beams you're running right now. Why do they call them pilot? And what's the difference between pilot beams and then the proper beams?
Yeah. So a pilot beam is in fact a single bunch beam. So in what happens later on in the LHC, once we're back in business for physics, we will have many packages of particles in the machine, which we call bunches. This can go up to 2,800 bunches per beam in either direction. For the moment, what we do, we have it only with one pilot, one bunch in the machine. And this we do because this is a safe way of setting up the machine. If we would start immediately with these thousands of bunches, as Steve already mentioned, the beam could be destructive for the machine. And since not everything is yet 100% sure to work flawlessly, we want to make sure that everything works before putting these multiple bunches in. So that's why we use pilot bunches.
Okay, so with this, I officially start the Q&A time, and I call back all our guests are here. We have you, Rende, in the CCC, but we have Romeo and Steve, who can also answer. The first question is for you, Rende, from Callum Bedson. Thank you, Callum, for asking this question. And it is, what's next for the LHC? Meaning, yes, now you have 3 weeks of pilot beam, this week +2, and then what's next?
So we have 2 weeks of pilot beam, then we stop again. And what we are also doing with respect to what we had in 2018 is that we're going to increase the energy of the LHC. So the energy of each beam before LS2, the long shutdown 2, was 6.5 tera electron volts. And now we're going to go to 6.8 tera electron volts per beam. And for this, we have to train the magnets. So these are superconducting magnets. So the temperature is 1.9 Kelvin, and they deliver a magnetic field of around 8 Tesla. Now, in order to reach that high magnetic field, you have to train these magnets. When you ramp up this field, there are tremendous forces in the coils of these magnets that can make slight frictions, and the slightest friction will increase the temperature in these coils, and that will make that the superconductivity is lost. Okay, so what we then do is we heat up the magnet, we ramp down the magnet, and the next time we exercise this ramp up again, this friction will not happen anymore at the same place because these strands of the coil have settled, but it may happen in another place. Okay, so and this is quite a lengthy process in order to train all the magnets. Now the majority of the magnets, so the machine consists of 8 sectors. 6 sectors have been trained up to 6.8 tera electron volts, and we still have 2 sectors that need to be trained in the coming months. So this will be one of the first things that we're going to do once we stop this pilot beam test again.
Okay, so there is another question. So what's the injection energy, and are you ramping the beam right now?
Excellent question indeed. So the injection energy is 450 GeV, which comes from the SPS, the super proton synchrotron. And since not all the magnets are trained, as I mentioned before, 2 sectors are not yet trained, we cannot ramp the magnets to high energy. So we decided to do all these tests at injection energy. So we keep the magnets at the standard fixed magnetic field, and all the manipulations and measurements we do will be done at this energy.
Great. I just so Adrian Guzman again. What is the new luminosity? Thank you, Adrian. Great question.
The new luminosity. So first of all, the luminosity we had in 2018 will be our goal to retrieve. Okay, so we had a big upgrade in the injector chain, and this will enable us to increase the instantaneous luminosity by a factor of 10, or over a factor of 10. But in order to be able to do this in the LHC, we need a second step in the upgrade. So we did now the upgrade of the LHC injector chain, but we also need the upgrade of the LHC towards the high luminosity LHC. And this is not yet done. So what we're going to do during the coming years is squeeze out the performance that was now, let's say, enabled by this injector upgrade program. So gradually we're going to increase the performance of the injectors. We're going to try and make use as much as possible of this performance in the LHC, but always keeping the machine, of course, in a safe situation. And only after long shutdown 3, which will take place in 2024, 2025, after that we will be able to profit fully from this high luminosity era.
So a step back into the past, I have a double questions for both of you. What have been the impacts of the ISR on future accelerators? So you can talk in terms of the magnets, and Steve then can talk in terms of operation.
For the magnets, I think it was really the introduction of superconducting magnets in the accelerator speed. Because already superconducting magnet existed in the physics experiments, let's say in the form of solenoids. But for the accelerators, the forces, the mechanical forces are completely different in their distribution with respect to what we have in solenoids. And this was a problem which was very difficult to solve. It has been solved by the Roman-Arch principle in the ISR.
That you showed
for
us
the
before.
The ISR superconducting quadrupoles. But this Roman-Arch principle has been then adopted by Fermilab for the Tevatron. Following my visit in Fermilab in September 1975, where I explained to the magnet experts, especially to their mechanical engineers, the principle, and they adopted that. And the following year, they built the first model working. Before they had several model magnets not working properly.
So superconductivity for magnets, and from your point of view,
so
what
the
was...
ISR was the big contribution.
Yes, and from your point of view?
From my point of view, there were many, many things which were discovered in the ISR and which were used in other accelerators. Probably the most important was something which is rather complicated, called stochastic cooling.
Right, you didn't mention stochastic cooling, absolutely.
If you have a beam which is going around in an accelerator and it's not bunched, you heard from Randy about the bunches. The beams have to be bunched in order that you can see the electromagnetic field with them and you can measure them. If the beam is coasting or debunched, there's no signal. So stochastic cooling allowed stochastic signals, Schottky scans we called them, allowed us to see the beam. And we saw the beam for the first time in the ISR, and that was a really wonderful moment because we knew we could see coasting beams, and immediately people started saying, if we can see them, we can act on them.
Yes.
And then stochastic cooling came around. And stochastic cooling became super important for the SPP bar S because Carlo Rubio had a proposal to collide antiprotons with protons. Now, the problem with antiprotons is, first of all, there's very few of them, and secondly, they're very large in distribution. And if you want to have a very high luminosity, you have to collide very tiny cross-section beams with each other so as to maximize the luminosity. And stochastic cooling was the only way to do that with the antiprotons.
And that was invented by Simon van der Meer.
That was invented by Simon van der Meer. In fact, it's a very wonderful story. He mentioned this in 1968 and didn't write it up. And when we saw the signals in the ISR, Wolfgang Schnell, my boss at the time, contacted him and said, "This is important, Simon." And Simon said, I'm too busy. But in the end, he wrote the report, and he even wrote at the end of the report, "I do not think this is practical, but I've written it up because the signals have been seen." And he got the Nobel Prize for that.
Yes, incredible.
It was very, very wonderful.
There is now
That was the key, really the key to antiprotons.
Yes.
There is now a question for Rende again. What will be the goal of high luminosity LHC?
Increase the discovery potential for the experiments. Okay, so what we will do is, from the injectors, we will produce brighter beams, so more protons per square millimeter. And these beams have to be preserved, this quality has to be preserved along the injector chain. And then it goes into the LHC, where around the experiments we squeeze the beam by using focusing magnets to even smaller dimensions, and then have these collisions. And that should produce this high luminosity in these detectors.
Okay, do we have candidate answers for our mysterious object? Shall we show it again? Can we show again the mysterious object? Yes. So if you're watching us now, this is an object. This is our mysterious object, and we welcome your answers. What do you think it is? And those who get close to the answer will win a section of an ISR magnet. So there is a question now for Steve. I mean, it's not for you, but I think you're the best place to answer. So all these skills at steering beams and becoming so knowledgeable and so precise, making them collide, apart from good science, great science and Nobel Prizes, what has it brought about?
Well, there have been a huge amount of spin-off from all of this. Probably, for me, the most important is the medical field. And there's been a lot in the medical field in terms of PET scans, et cetera. Since I've been retired, I've been working on a proton accelerator for cancer therapy. And this originated at CERN, originally under Ugo Amaldi. Ugo and I worked together in the ISR, so it's very interesting. And
yes.
His team started it, and now we are producing it in a company to make it a commercial product. And that should be available by next year, and it will greatly improve the treatment of cancer patients.
Amazing. So there's not a chance. That's not by chance. That's absolutely because you and Ugo both worked in that field. And there is a practical example now in Italy, which is celebrating, I think it's 20th anniversary this year. And they've, I don't know how many patients they've cured with proton beams and ion beams. So instead of a target, you have a patient. Instead of colliding beams, you bring a beam precisely on the cancer of the patient.
Kill a cancer tumor with a proton beam is basically what you do.
Okay, so we have somebody who proposes an answer. Can you tell me what the answer, Prabhanyan Mrutike, I hope I pronounce your name well. So what does he think the mysterious object is? And let's show it once more. What does he say it is? So our jury will discuss. So, Prabhanyan Mrutike, thank you for trying solving this riddle. And I'm asking the social media to tell me what's the answer he proposes. That it is what? He says it is a magnet. Is that correct?
Yes, it is in fact the split field magnet. In fact, this object, the split field magnet, which had a length of 10 meters, a weight of 1,200 tons. So
yeah, it says SFM spectrometer. Is that? It's even more precise than a magnet.
Split field magnet.
Split field magnet.
Spectrometer, yes.
Spectrometer.
And it was located just here.
Just here.
Yeah, that's why we chose it, because it was the object that was located here.
It was filling up
The whole hole.
completely, because there was the magnet itself plus compensator magnets and magnetic channels. It was very...
So congratulations, send us your address so that we can send you the gadget. And I think on this happy note, we can conclude this live. I would like to thank all our guests, Steve Myers, Romeo Perim, Randa Sterenberger, that interrupted your work at the CCC. Thank you for letting us invade the control room.
With pleasure to share this.
And the technical crew behind the cameras, the social media team, but most of all, our viewers. We will not go away. Now the LHC adventure has started again, so we will follow every step of it and go live every time it's possible. So stay tuned and watch our channels and keep asking your questions, because our experts can work even after the live and send you their answers. Thank you for viewing, and until next time.